Welcome to Xiaol.x. This is the overview of SSA, Sparse Sparse Attention. We'll explore why applying sparsity twice unlocks efficiency, scalability, and precision in modern transformers. Think of this as the warm-up. A full podcast conversation dives deeper.
Ditch. Standard AI models completely collapse on long documents. I'm talking 0% accuracy. Literally zero. Once the context gets big enough. As the pages stack up, the model implodes. Look at this. Performance falls off a cliff and slams into nothing. But a new long context architecture...
Here's the paradox. When a token is masked out of the loss, gradients never flow back. It's like the model never hears that word, so it never learns it. Researchers flip the script with self-sparring adaptation, or SSA. A heavy, accurate brain trained side by side with a lightweight note.
Imagine training two minds at once, a big, precise thinker and a quick, lightweight note taker. SSA's breakthrough is simple. During training, the heavy model watches the light one work and learns its shortcuts. The result? The same performance in a fraction of the time, about 6 times faster.
Welcome back to the Deep Dive. Today we are taking a rapid journey right to the bleeding edge of large language model efficiency. We're specifically tackling that massive headache of context length. I mean, it feels like every month there's a new LLM that promises to handle bigger and bigger documents.
Oh, absolutely.
Processing a whole novel or an entire code base, you know.
That's the frontier, without a doubt. We've seen the industry go from, a standard 4,000 tokens just a couple of years ago, to now systems are claiming they can handle 128K, even 1 million tokens.
But that scale always seems to hit the same wall.
It does. Yeah. The same fundamental computational roadblock. So this week, we're unpacking a research paper that tries to blast right through that wall. It's called SSA, Sparse Sparse Attention, and it's from researchers at King's College London and Tencent U2 Lab.
So our mission today is to really get under the hood of their novel solution.
And, here's the hook for you, the listener. Have you ever wondered why processing a document that's, say, 50,000 or 100,000 words long is just so hard for even the best AIs?
Right.
The problem lies entirely in the way the core of the AI, this thing called the self-attention mechanism, has to operate. It's what drives the cost up to, pretty much impossible levels.
Okay, so let's unpack that. We have this huge demand for long context. Let's start with the old way, the traditional method, which these researchers call full attention.
Right. Full attention is, it's intuitive, but it is computationally devastating.
How so?
Imagine you have a 1,000-word document. Every single word or token in that document has to look at, calculate, and interact with every single other preceding word.
To figure out its meaning in context.
To figure out its meaning, exactly. It's comprehensive, but it's just completely inflexible.
And that's where the roadblock gets serious. So if we say the context length is n, the computational cost of that attention calculation increases quadratically. So n squared.
Exactly. We call that quadratic complexity. And to put that in, plain terms, if you double the length of your text, say, you go from a short essay to just a small book chapter.
The cost doesn't just double.
No, not at all. It balloons out by a factor of 4. So you can imagine trying to process a 100,000 token document. The cost it goes through the roof, becomes computationally prohibitive, and it locks us out of any true long context reasoning.
So the solution then, the one people have been chasing for years, is sparse attention, or SA. The idea is to restrict each token so it only interacts with a select important subset of other tokens.
Yeah.
It feels intuitive, right? Like how a human reads. You don't read every single letter of a textbook to get the main idea. You scan keywords, topic sentences.
That is exactly the goal.
Yeah.
But here is where the paper gets really fascinating. The researchers identified this critical paradox with the previous attempts at sparse attention.
You mean models like MoBA or NSA?
Yes, those. While those models did succeed in, cutting down the raw computation, they suffered from what the paper calls severe performance degradation.
Wait, I remember this point. It's just stunning. They found that models trained specifically for sparsity, they unexpectedly ended up with lower inherent attention sparsity than the old full attention models.
Isn't that wild? It's the central mystery they set out to solve. How is a model trained to be sparse actually less selective?
So, to be clear, when we say attention sparsity, what does that mean?
It's a measure of how selective the model is. Basically, what fraction of the total attention energy is contained within the few most important tokens it chose to look at.
And higher is better, more focused.
Higher is much better. And the data was clear. The classic full attention baseline had a mean attention sparsity of about 0.630. But these previous sparse models, they had a lower mean, around 0.583. They were trained for efficiency, but they completely failed to learn how to be selective.
So what's the failure? What's causing this paradox? The paper points to something called a gradient update deficiency.
This is the key mechanical insight. Think about how that old sparse training worked. To save time, the model would just aggressively exclude tokens it thought were uninformative. It would just throw them out of the calculation.
Okay.
But here's the flaw. If those tokens are completely excluded, they receive no forward signal and, crucially, no backward gradient.
Meaning, what is that? What does that do?
It means the model never gets the full picture. More importantly, it never receives the necessary negative feedback. It's like trying to teach a student what to ignore in a 100-page book, but you only ever show them the key paragraphs.
Ah, I see. They can't learn what's unimportant if they never see the unimportant parts.
Exactly. They can't learn the lesson of suppression. So the model fails to learn how to effectively downweight or ignore those uninformative tokens, which just cripples its ability to generalize. It gets messy.
Okay, so that clarifies the deep problem here. The model needs the efficiency of being sparse, but it absolutely needs the complete gradient flow from full attention to actually learn what's noise and what's signal.
Precisely. And that is what makes this new SSA solution so clever.
SSA, which stands for Sparse Sparse Attention.
Right. It's a unified training framework that's designed specifically to fuse the efficiency of sparsity with the learning stability of full attention.
So how do they pull off this fusion? The paper describes a dual-stream training approach. It's like having two paths working side by side during training.
That's right. So at every single training iteration, the model randomly picks one, either the full attention stream or the sparse attention stream, with a 50% probability to do the main task. But that's just the foundation, the real genius. The real magic is what they call the bidirectional alignment mechanism.
And this is the part that forces the two streams to stay consistent with each other at every layer. It's done through something called an alignment loss.
Yes, and this alignment loss, it has two components that act almost like, well, like opposing forces, but they harmonize with each other.
Okay, so tell us about the first force, the sparsity loss.
The sparsity loss. This one encourages the full attention output to mimic the sparse attention output. Okay, so think of the full attention model as this comprehensive, detail-oriented student, and the sparse attention model is the efficient, high-level note-taker. This loss forces the detail-oriented student to learn from the efficient one. You're basically teaching the heavy, full attention mechanism how to become inherently sparser, more selective.
So you're forcing the full model to learn efficiency. That must be how they fix the paradox. And the second force is the commitment loss.
Right. And if the sparsity loss is forcing efficiency, the commitment loss is, it's like a safety harness. It's a governor. It regularizes the sparse attention output to stay consistent and close to the reliable full attention output.
Ah, so it stops the sparse path from just going completely off the rails.
Exactly. It prevents the efficient note taker from drifting, from becoming unstable, or from just guessing wildly because it has incomplete information, which, by the way, was the huge pitfall of all those previous sparse-only models.
So you've got stability on one side and you're enforcing selectivity on the other. It's an elegant mechanism. The gradient deficiency is fixed because the full attention stream is always there, teaching the model what to suppress. And at the same time, this alignment is explicitly pushing for the highest possible sparsity. So you get efficiency without that performance hit. The theory sounds great, but did it work?
Oh, it worked. The results are, well, they're pretty definitive. What this bidirectional forcing delivered was something really remarkable. It didn't just solve the sparsity paradox, it delivered state-of-the-art performance.
So let's talk about that first key result. This demo number one for anyone following along with the paper, the proof that they conquered the paradox.
Okay, so they measured the inherent attention sparsity after training was done, an SSA. It attained the highest attention sparsity across all layers, with a mean of 0.706.
And that's way higher than the traditional full attention model's 0.630. And it just absolutely dwarfs those older sparse attention models, which were stuck down at 0.583.
It does. It's a huge jump. By forcing the model to align its full and sparse outputs, they literally taught the full model how to be better at ignoring irrelevant data.
So the constraints actually made the model fundamentally more selective, not just computationally lighter.
That's the key takeaway. And that increase in sparsity translates directly to better decision-making, right?
It has to.
It does. When they tested it on common sense reasoning benchmarks, SSA achieved state-of-the-art results, which strongly suggests that a sparser, cleaner attention distribution leads to less noisy, more precise thinking. The model isn't being distracted by junk in its context window.
Okay, now for the second key result, and this one speaks to practicality. SSA offers these incredibly flexible compute performance trade-offs.
Right. So they measured performance things like reasoning accuracy and also perplexity, or PPL, as they changed how many tokens the model was allowed to see during inference.
Basically cranking the dial on the computational budget.
Exactly. And what they found was that SSA's performance consistently and smoothly improves as you give it access to more context. It shows really robust generalization across all budgets, from super sparse to full attention.
And the competitors?
Well, the competitors often failed to do that. Their performance would plateau or sometimes even get worse when you gave them a bigger budget, which suggests they just hadn't really learned the structure of the data reliably.
Now, the third and maybe the most critical result is all about extrapolation. And this is where the paper gets, really interesting. The models were all trained on a standard 8,000 token context. But the real test is what happens when you suddenly throw a massive, totally new context at them, like 32,000 tokens.
And this is where you see the catastrophic failure of the standard full attention baseline. They call it full-atten.
It just collapses.
It completely collapses. Past that 8,000 training length, it's over. For example, on a really tough task like needle in a haystack retrieval.
Finding one fact hidden in a giant document.
Right. Full-atten hits 0% accuracy at 16,000 and 32,000 tokens. It forgets how to find things, and its perplexity just explodes.
And that brings us to demo number 2, which is just this killer visual from the paper. It's the graph of the perplexity curves. You see, the full-atten model's perplexity is fine up to 8K, and then it just shoots up like a rocket.
It's a vertical line, almost, while SSA's PPL curve just stays stable and low all the way out to 32,000 tokens. It's just a flat, calm line.
So if the model is ignoring the useful tokens later on, is that why its retrieval accuracy drops to 0? Because it literally cannot see the needle anymore.
That's exactly right. And the root cause is this pathological behavior they identified called the attention sink phenomenon.
That sounds bad. What is an attention sink?
It's a technical term for a catastrophic error. When the context length gets much bigger than what it was trained on, the standard full-atten model starts to over-concentrate its attention on the very first tokens in the sequence.
The ones at the very beginning.
Yeah, often just the first few tokens, which are usually just placeholders. And it develops these extremely severe global spikes in its attention scores. It's like a person panicking under information overload and just staring blankly at the first sentence of the document, completely missing the actual content.
And this is our third demo, right? The comparison of the attention score distributions. The visuals are so stark.
They're incredible. At 32,000 tokens, you look at the full Essen distribution, and it's just dominated by these massive data-independent spikes at the beginning. And those spikes suppress all the attention that should be going to the local informative tokens later on.
SSA.
But SSA maintains a clean and stable distribution. It still gives attention where it's due, but it avoids those runaway global spikes. It keeps its focus on local tokens throughout the entire document, and that robustness is what allows it to keep its perplexity low and its performance high, all the way out to 32,000 tokens and beyond.
It proves SSA trains a model that just generalizes to long context much, much more effectively.
However, for all its robustness, the paper is pretty clear that SSA isn't. It's not a magic bullet. It requires some careful tuning.
Right. There's always a catch.
There's always a catch. And achieving optimal results is actually quite sensitive to certain hyperparameters.
So what kind of sensitivities did their ablation studies turn up?
Well, the main one is balancing the optimal size of the receptive field. That's just how many tokens the sparse attention path is allowed to look at.
Okay.
And they found that forcing a tighter focus, so using a smaller receptive field like 16 by 16, actually provided stronger regularization and better final results than allowing a bigger field like 32 by 32.
So being more aggressive with the sparsity helps.
It seems to. It suggests the regularization from that sparse stream is most effective when it is aggressively sparse. It really forces the full attention path to be disciplined.
And the alignment loss itself, I assume that's completely indispensable.
Oh, absolutely. Taking away the bidirectional alignment loss entirely caused, and I'm quoting here, considerable performance degradation and unstable training.
So that confirms it. The back and forth constraint between the two paths is the whole secret sauce.
It's fundamental. It can't work if the two paths don't learn from each other.
And what about efficiency? Because the model is computing these two streams, does that mean the training cost is doubled?
Thankfully, no. The training cost is only marginally increased. And that's because the model computes that auxiliary output only for the alignment objective. It avoids doubling the overall compute for the main training task. So it's a very slight increase in training cost for this massive gain in inference efficiency and stability.
So wrapping up, what does this all mean for the big picture? I mean, the breakthrough here is that SSA solved that critical paradox.
It did.
They successfully integrated the best of both worlds, full attention, stable gradients, and sparse attention's efficiency, all through this really ingenious output alignment.
And that gave them both the highest inherent sparsity and state-of-the-art long context generalization.
The overarching lesson here is, for me, maybe the most provocative thought of all. The research seems to suggest that forcing LLMs to think in a sparser, more selective way during training makes them fundamentally better thinkers.
I think that's right. The fact that SSA has an advantage even when you run it in full attention mode for inference, that proves that models with sparser attention distributions are just less influenced by irrelevant noise.
Leading to better reasoning and robustness against these attention sink problems.
Exactly.
AI, the first frontier. This finding that constraints, specifically this structural sparsity, can actually lead to better, more robust, more intelligent models, that really changes how we approach efficiency and generalization in these systems. The future of giant competent LLMs isn't about how much information they can densify.
No, it's about intelligently and effectively managing what they choose to ignore.